we now have the building blocks of an artificial neural network, the so-called neuron. And what we've seen is that it is not that dissimilar to things we have seen before. We start with a linear model, take our inputs x, multiply them by some weights w, which we need to learn, get some output, optionally put that output through some nonlinearity, a sigmoid, a binary output, or a rectified linear output, and then try to do supervised learning. Map some inputs, 1 through xn. We're going to get an output here for a set of weights, and we want those to match the desired labels associated with each of the inputs. It's a supervised learning problem. And right now, it doesn't look like anything different than what we've done before, but you'll see we'll start putting these pieces together in a more sophisticated and complicated way. And in particular, this nonlinearity is going to play a very critical role, as we will see. Well, let's start off by asking the same question we've been asking. We've got a model, linear model with an optional nonlinearity. We want to learn something, so we set up an objective function, and then we want to minimize that objective function. So let's start there and then see what happens as we build up more and more sophistication into these neural networks. So here we go. My model is y is equal to a sum, wi from I equals 0 to n, times the data x of I. And again, remember, I'm setting x0 to 1 so that the 0th element here is just the constant term. Y hat is the result of pushing that output of that linear model through an optional nonlinearity, which for now we will assume maybe linear, maybe sigmoidal, maybe something else. Let's not worry about it. Okay, so what does the supervised learning tell you? I give you a bunch of data, x1 vector up to xm vector. I have m samples. They're each vectors of dimensionality n. I have associated with each of those inputs some output label, z1 to zm. If it's a two-class classifier, some of the labels will be -1, some will be 1, or some will be 0 and some will be 1, depending on how you want to classify it. So my input is a labeled training set. The data itself is x1 to xm, and the labels are z1 to zm. And now what do I want to do? I want to establish an error that I want to minimize. Well, what should be our first error? Well, we know what our first error should be. It should be the quadratic error because we know how to minimize that. So let's establish a quadratic error. I'm going to ask, find me the w. So this is an error in w, the vector w, which are the weights associated with my model. By the way, I assume I tell you what the nonlinearity is. You're not learning it as we did, for example, in an SVM. So it's going to be the sum over all data, k equals 1 to m, of the label associated with the mth data point minus the label that my neuron hands me back, which is f, the nonlinearity or the linearity, applied to x transpose w, which is just the model here. So I evaluate my model, I push it through a nonlinearity, I take the difference from the actual label, I square that and I sum everything up. And what happens at the end is I have a quadratic error surface. How do I know that? Because I have a quadratic error. And we know what to do here. We can do least squares if the system isn't too big. We can do steepest descent. We can do conjugate. We can do gradient descent. We can do whatever we want. How do we do it? Take the derivative, set equal to 0, and solve. So let's just go ahead and do that. Take the derivative of this, and let's see. What are we differentiating with respect to? W, the weights associated with the model. So the 2 is going to come out here, so we get the 2, times zk minus this whole thing, so that's this guy right here. But notice here that w is inside of here, so now we need to do the chain rule. So what's going to happen here is it's the derivative of this with respect to w times the derivative of f with respect to w. So I've got the derivative of what's inside here with respect to w. Well, that's just the x sub k. And notice here I've broken this out of the vector notation to make it a little bit easier, times the derivative of f with respect to w. Okay? And notice here, by the way, I've got an I index because now I'm taking the partial derivative of w with respect to the ith value of w. So let me come back and emphasize this again. This is not the full derivative, it's the partial derivative of the ith weight. Why am I doing that? How many weights do I have? I have n of them. There it is right there. And I want to know for each w separately, how am I going to determine what that w is? So I take the partial derivative of this, and that's why here only the ith term of x matters, because when I take the derivative of this with respect to w, only the ith term here matters, and I grab the ith term of x here. So here is the derivative with respect to the ith component of my model. What do I want to do with this? I want to set equal to 0. Of course I do. So let's go ahead and set this equal to 0 and solve. And this thing right here now, which is just I've taken out the 2 over here and I've replaced it with an alpha. I'll come back to that in a little bit. Is just the combination of my actual label, the nonlinearity associated with the data times the model parameters, and the derivative of the nonlinearity. This is the so-called delta rule, which tells me how to move through this quadratic error space in order to do the minimization of each of the w's. So let's see what that looks like by instantiating the f. So let's go back up. I've got the delta rule here. This alpha here is the weight. So if you remember when we were talking about iterative least squares and steepest descent, there was that notion of you pick a direction in the space and you move in that direction. That's what this is going to be. And then you evaluate this as well. Let's play with let's assume that the nonlinearity is non-existent. So f is just going to be linear, and let's see what happens to this delta rule. Well, let's see. Here, f of x transpose w is just x transpose w. And the derivative of f, well, it's a linear function, so the derivative is just 1. There's nothing happening here. So this term goes away, and this term just collapses to x transpose w. So now my delta rule, which is how do I update w on each iterative solution of this, is going to be the sum over all the data points, 1 to m, of alpha, that's my step size in the going down that quadratic error surface, of z sub k, that's my label of my labeled data set, minus the dot product between my data and the model times the ith component of x, because that's the ith component that I'm iterating over. Okay, so what have I done here is I didn't do the full-blown least squares because when these systems get very, very big, I'm foreshadowing a little bit, we're not going to be able to do least squares. The matrices are simply way too big for the computations. And we are not going to do steepest descent where we actually compute the full-blown, the right direction size and the right step size. We are going to do steepest descent, gradient descent rather, where we move down that surface in small increments for each of the weights until we get to the minimum of that quadratic, because that's the most efficient way to train or learn the weights associated with the neural net. So let's see, we can actually write this for a simple problem. We can write the learning of the weights. So here we go. I'm going to just do 3 weights. So I'm going to assume that my input is x0, 1, x1, x2. Okay? I'm just going to take 10 observations. I'm going to generate some random weights, which are going to be the starting condition for this nonlinear iterative least squares, which we've already seen. I'm going to generate my data matrix here. I'm going to generate my labels, z here, by applying the weights to the data. And then I've got a learning rate. And remember that this learning rate is very, very delicate. Make it too small, and the iterations are going to be very, very slow, and you'll take forever to get to the minimum. Make it too big, and you're going to overshoot and create instability. And this is going to be part of the black magic of training neural nets, is figuring out what that learning rate is. Here is the random starting conditions for the weights. Sorry, I think I misspoke here. This is the actual weights of the model, and then these are the labels associated with the weights. This is a random starting condition. So again, I'm in some space. I have a quadratic error function. I pick a random position, and I'm going to move slowly down to the minimum. How am I going to move? Here's my delta rule. For some number of iterations, which I've fixed at 500 here arbitrarily, I'm going to compute z minus w times x. That was the delta rule because I'm assuming a linear no nonlinearity, so that f was linear. I'm going to take each w here in my model and update it according to the rule. There it is right there. I'm going to print the w and the w0 so I can see what's happening for the real weights and the estimated weights. And this is essentially an iterative least squares with a hardwired weight in order to learn the weights with and this is important, no nonlinearity after the linear model. Now, what did I just do here? I wrapped around a lot of new words, neurons, for example, but we haven't actually done anything new. This is basically iterative least squares. This is gradient descent. We're back to sort of where we started. But now when I add in some nonlinearities, things are going to change a little bit because that delta rule is going to look a little bit different. By the way, one of the reasons why we did iterative least squares and steepest descent and conjugate descent and gradient descent is because that's the machinery we're going to need to train neural networks. And by the way, training, I've never liked that word very much. We're just learning the weights. Right? We're learning the weights the same way we did with least squares. It's just that as these systems get big, we have to be a little bit more clever in terms of the optimization. So it's always good to remember that there's no real brand new concepts here with these neural networks. It really is that we're taking ideas that we've already seen and that have been established for a long time, and we're going to put them together in slightly different ways to get more power out of them. And that's what we'll see as we keep going down this road of thinking about artificial neural networks.